Hello, my name is Brendan Han, and today I'll be doing a lesson on projective geometry. So in today's lesson, I'll be covering 5 topics: cross ratios, harmonic ranges, harmonic pencils, harmonic quadrilaterals, and poles and polars. And I will be going through some important theorems, and at the end, I'll be solving some questions using these concepts. So first, I'll be covering cross ratios. So say that there are 4 points A, B, C, D on a line. And then the cross ratio of ABCD would be AC times BD over BC times AD. And here it is important to note that ABCD do not necessarily have to be on a line in that order. For instance, it can be AC, BD, or AD, BC. So the first lemma says that if A, B, C, D are points on line W, for any line L and any point H where H is not on lines L or W, if we say that K is the point where H, A, and L meet, L is the point where H, B, and L meet, M is the point where H, C, and L meet, and N is the point where H, D, and L meet, then A, B, C, D, and K, L, M, N have the same cross ratio. And this can be proven by manipulating the area ratio of the triangles. So what are harmonic ranges? If we say that on the line, there are 4 points A, B, C, D in that order, A, B, C, D is a harmonic range if and only if AB over BC is equal to AD over CD. In other words, ABCD is a harmonic ratio if and only if the cross ratio of ACBD is -1. For simplicity in this presentation, I'll be saying that if ABCD form a harmonic range, ABCD is harmonic. So there's a tool called Harmonic Pencil that's used very often in projective geometry problems, and it states that if A, B, C, D are points on line W where A, B, C, D are harmonic, for any line L and any point H where H is not on lines L or W, if we say K is the point where H, A, and L meet, L is the point where H, B, and L meet, M is the point where HC and L meet, and N is the point where HD and L meet, then K, L, M, N are also harmonic. And this can be shown by using Lemma 1. So harmonic quadrilaterals are a very special type of quadrilaterals, and their definition is a harmonic quadrilateral is a quadrilateral inscribed in a circle that satisfies AB times CD is equal to AD times BC. And there are 2 very important properties when it comes to these quadrilaterals. The first property is that AC and the tangents of points B and D are concurrent. And the second property explains the relationship between harmonic ratios and harmonic quadrilaterals. The lemma states that if ABCD is a harmonic quadrilateral inscribed in circle O, for any line L and any point G where G is on circle O, if we say that H is the point where GA and L meet, I is the point where GB and L meet, J is the point where GC and L meet, and K is the point where GD and L meet, then HIJK is a harmonic ratio. And this can be shown by manipulating the sine ratio of the different angles. So what are poles and polars? For any point A, define A prime such that A prime is the inverse of A around circle O. The polar of point A is the line perpendicular to OA that passes through A prime, and A is the pole of the polar line of A. So when it comes to poles and polars, the most important theorem is a theorem called Lahir's theorem, and it states that if point B is on the polar of point A is also on the polar of point B. And the proof is quite straightforward. It states that let's first put B as a random point on the polar of point A, and put A prime as the inverse of A and B prime as the inverse of B. And if you say that R is the radius of circle O, by the definition of inversion, OA times OA prime is equal to OB times OB prime, which is equal to R squared, which means that A prime, B prime is concyclic. AO and BA prime are perpendicular, which means that OB prime and AB prime are also perpendicular, which means that by definition, AB prime is the polar of point B, and A passes through the polar of point B. Now, using Lahir's theorem, we can find some very interesting properties of poles and polars. The first property is that if B and C are the tangents to circle O from point A, then BC is the polar of point A. And the proof goes like, if you put R as the radius of circle O, then OB equals OC is equal to R. and B is the inverse of B around circle O, and C is the inverse of C around circle O. And by definition, BA is the polar of point B, and AC is the polar of point C. By Lahir's theorem, BC is the polar of point A as A passes through the polars of points B and C. The second property shows the relationship between harmonic ratios and poles and polars. It states that A is a random point outside of circle O, and E and F are the tangents drawn from point A onto circle O. B is a random point on minor arc EF, and ray AB meets circle O at point D. For some point C on BD, ABCD is harmonic if and only if C is on the polar of point A. The forward proof is quite straightforward. It states that if we assume that C is on the polar of line A, then ECF is collinear because by lemma 3, EF is the polar of point A. EBFD is a harmonic quadrilateral because the tangents of E and F and DB meet at one point, which is point A. And by pencil of EBFD through point F onto segment AD, we can see that ABCD is a harmonic ratio. The backwards proof works in a very similar way. If we assume that ABCD is a harmonic range and C prime is the point where AD and EF meet, as previously shown, ABC prime D is harmonic, which means that both ABCD and ABC prime D are harmonic. Hence, C and C prime are identical. C is a point on EF, and EF is the polar of point A, which means that C is a point on the polar of point A. So now I'll be going through 6 questions using these concepts. The first problem is a very important theorem when it comes to poles and polars, and it states that if ABCD is a cyclic quadrilateral and circle O is the circumcircle of ABCD, and E is the point where AC and BD meet, and Q is the point where DC and AB meet, and P is the point where CB and DA meet, we are trying to prove that O is the orthocenter of triangle QEP. So if we put L as the point where PE and AB meet, W as the point where PE and CD meet, R as the point where QE and BC meet, and S as the point where QE and AD meet, then QCWD is obviously harmonic, and this can be shown by using Seva and Menelaus's theorems. By lemma 2, point W is on the polar of point Q. And by pencil of QCWD through point P onto segment QA, we can also see that QBLA is harmonic, which means that by lemma 2, L is on the polar of point Q. Hence, LW is the polar of point Q. Similarly, RS is the polar of point P. And by definition, this means that OQ and PW are perpendicular, and OP and QE are perpendicular, which means that O is the orthocenter of triangle QEP. The second problem is quite a challenging question. It states that if PQRS is a cyclic quadrilateral with center O, A is the point where the bisectors of SPQ and PSR meet, B is the point where the bisectors of SPQ and PQR meet, C is the point where the bisectors of RQP and SRQ meet, and D is the point where the bisectors of SRQ and PSR meet. If W is the point where PR and SQ meet, X is the point where QP and SR meet, and Y is the point where SP and RQ meet. If O1 is the circumcenter of triangle ABD, we're trying to prove that O, O1, and W are collinear. So first, we have to prove that ABCD is concyclic, and this can be shown through simple angle chasing, as angle DAB plus angle DCB is 180 degrees, which means that O1 is not only the circumcenter of ABD, but O1 is the circumcenter of ABCD. By problem number 1, W passes through the polar point X and the polar point Y, which means that by Lahir's theorem, W is the pole of XY. By definition, OW and XY are perpendicular. C is the incenter of triangle XRQ, and A is the excenter of triangle XPS, which means that both A and C pass through the bisector of angle SXP. If we put angle XPS as 2A, then angle SRC is equal to XAS, which is equal to A, which means that ASRC is concyclic. By power of a point, we can see that XA times XC is equal to XS times XR, which means that X is on the radical line of circles O and O1. Similarly, we can see that Y is on the radical line of O and O1. Therefore, XY is the radical line of the two circles, and OO1 and XY are perpendicular. In conclusion, OO1 and XY are perpendicular, and OW and XY are perpendicular, which is that OO1 and W are collinear. The third problem is a question from the 2006 China Western Math Olympiad, and it states that, as in the figure below, AB is a diameter of a circle with center O. C is a point on AB extended. A line through C cuts the circle with center O and D and E. OF is the diameter of the circumcircle BOD with center O1. Line CF intersects the circumcircle again at G. We're trying to prove that O, A, E, and G are concyclic. So first we have to put Q as the point where AD and BE meet, P as the point where BD and AE meet, and R as the point where CQ and PO meet. If OGP is collinear, then PE times PA is equal to PD times PB, which is equal to PG times PO, and so EGOA is concyclic. Hence, if we prove that R and G are identical, the proof is over, as it means that OGP is collinear. By problem number 1, RQC is the polar point P, which means that RC and OP are perpendicular. FGP is also 90 degrees as OF is the diameter of circle O1, which means that R and G are identical. Hence, the proof is complete. The fourth problem states that for any point A outside of circle O, AB and AC are the tangents drawn from A to circle O. Here, draw a random line L and say that line L meets circle O at points D, F, and meets segment BC at E. Here, prove that FD is the symmetrion of triangle CBF. So first, by lemma 2, ADEF is a harmonic range. By pencil of ADEF through point C onto circle O, DCFB is a harmonic quadrilateral. Therefore, CD times BF is equal to BD times CF. By Ptolemy, we can see that BC times DF is equal to 2CD times BF, which means that MB times DF is equal to BF times CD. Hence, MBF and CDF are similar to SAS, which is that DF and MF are isogonal regarding point F in triangle BCF, and so DF is the symmetrion of angle F in triangle BCF. The final question states that ABCD is a harmonic quadrilateral inscribed in circle O, and P is a random point on circle O. Call LP the tangent line of point P, LA the tangent line of point A, LB the tangent line of point B, and LC the tangent line of point C, and LD the tangent line of point D. If you put A1 as the point where LA and L meet, B1 as the point where LB and L meet, C1 as the point where LC and L meet, and D1 as the point where LD and L meet, we're trying to prove that A1, B1, C1, D1 is harmonic. So put A2 as the midpoint of AP, B2 as the midpoint of BP, C2 as the midpoint of CP, and D2 as the midpoint of DP. Here, obviously, we can see that A2, B2, C2, D2 is homothetic when ABCD with P as the homothetic center, which means that A2, B2, C2, D2 is also a harmonic quadrilateral. Obviously, O, A2, B2, C2, P, and D2 is concyclic, which means that lemma 2, A1, B1, C1, D1 is harmonic. So thank you for watching. This was quite an advanced topic, and I hope this wasn't too challenging. Thank you.